So this is topic I, Unit 2, Topic I, Part 2. We've been looking at implicit derivatives, and we're now going to look at an application. We'll take the ellipse, 9x squared plus 16y squared equals 144. Notice this certainly is in implicit form, and it's not real convenient to solve for y. This is one of those where if I tried, I'd have a plus or minus, which is sort of ugly to work with. So we're going to stick with the implicit form. And my first goal is to find the equation of the tangent line at the point 2, 3 square root 3 over 2. So, as always, to find the equation of a tangent line, I need a slope and a point. They flat out gave me the whole point this time. I don't have to do any work there. And so I will concentrate on finding the slope. To find the slope of the tangent line, I need dy dx. And to get dy dx, I'm going to do an implicit derivative. So the derivative would be 18x plus 32y times dy dx for the chain rule piece equals 0. I need to solve for dy dx. So 32y dy dx equals negative 18x. And if I divide by 32y, dy dx would be, what, negative 9x over 16y? And so to find the actual slope that I want, I'll simply plug the x and the y values in there. 2 for x, and 16 times this, not such a great but workable number, 3 square root 3 over 2 for y. And this is not going to come out very pretty, so I'm just going to get a decimal approximation for that. And I got negative 0.433. My point was completely given, so I've got an x and a y. And let's just go ahead and get a decimal approximation for that y value as well, so that when I put it into my equation for a line, it's not quite so bad. 3 square root 3 divided by 2 is about 2.598. So, equation of the line, y equals mx plus b. Put in my y value, my slope, times the x value of 2. So I've got 2.598 equals negative 0.866 plus b. And we'll add there to get a b value, 3.464. So my tangent line is y equals negative 0.433 x plus 3.464. All right, let's take a look at part B. Where does this ellipse have a horizontal tangent line? Horizontal tangent line, of course, would mean the slope would be 0. And so if I take my function that represents slope, dy dx, and I ask myself, where is that slope or derivative equal to 0? Well, I could multiply both sides by 16y, and that would just give me negative 9x equals 0. So when x equals 0, I should have a horizontal tangent line. I'm going to answer part C, and then we'll go ahead and we'll take a look graphically at, actually we'll look back at all three of them, A, B, and C. So in part C, where does the ellipse have a, whoops, and that's a typo, that should have been a vertical tangent line is what I really meant to ask there. Copy and paste here. Where does this graph have a vertical tangent line? Well, as far as a vertical tangent line is concerned, what's the slope? For a vertical line, slope's undefined, right? So once again, I'm going to say I already calculated my slope function, which is the derivative. And that's going to be undefined if the denominator is equal to 0. So if 16y is equal to 0, or in other words, if y equals 0. So I would be expecting a vertical tangent line at y equals 0. Okay. All right, let's take a look at the graph of this ellipse. And I think I've actually got that done on Desmos already. There it is. We've got our ellipse, 9x squared plus 16y squared equals 144. And if I start by taking a look at these last two things we said we expected a horizontal tangent line at x equals 0. Notice right here, where x is 0, the tangent line would be horizontal. And also right there, where x equals 0, we'd have a horizontal tangent line. If we wanted to, we could even graph them. It looks like it's y equals 3 and y equals -3. And you can clearly see those horizontal tangent lines right at those points where x is 0. So those two look good. We also predicted vertical tangent lines at the points where y equals 0. That would be there and there. Again, pretty clearly, the tangent lines would be vertical there. If I wanted to, I could graph them as x equals -4 and x equals +4. And once again, you can really see the tangency at those 2 points. All right, as long as we've got this graph here, let's go back to part A for a moment. We found the equation of the tangent line at a given point. Let's graph that tangent line too, just so we can verify. It was -0.433x plus 3.464. And you can see right here, there's just about our point of tangency. It looks like I'm off just a little bit to move it over just a touch. Maybe I'm not going to get it exact, but you can see that the tangent line is just about here at 2, 2.6. Just didn't hit it right when I clicked on it. There it is. Almost. Thought I had it. Well, you get the idea. It's hard to click on the exact spot on Desmos that I want, but you can definitely see that the line we found certainly looks tangent to the ellipse. All right, that brings us to the end of section I.